water versus surface volatiles. So my work focuses on apatite, and you may have heard at LPSC there's a little bit of controversy going on with the water content of apatite. The problem is, as Jeremy Boyce showed, that the partitioning of fluorine, chlorine, and hydroxyl into the halogen site in apatite is a lot more complicated than we initially thought, and we really can't use apatite to calculate water content of the melt that the apatite came from. So when I talk about water content here, it's water content of the apatite, which might be sort of related to how much water is in the melt, but it's not. I'm not saying that I have 7,000 ppm H2O in any of these melts. It's just we're looking at it from kind of a relative standpoint that Mare basalts may be more water rich than some of the evolved compositions. Apatite on the moon varies in delta deuterium, which is a measure of deuterium versus hydrogen against a terrestrial standard, for those of you who may not be as familiar with isotope notation. On the y-axis, there's a huge range in delta D on the moon, up to over 1,000 per mil, all the way down to minus 500 per mil. That's work I showed at LPSC this year, and I'm going to be building on today. So this plot's pretty confusing. Right now I have, this is all apatite data taken by all the different groups working on apatite right now. Delta deuterium versus parts per million H2O. 5,000 ppm H2O is equivalent to 0.5 weight percent H2O. Everything is up here is by rock type, so the Mare basalts are these gray diamonds. A lot of these colored points are more evolved compositions. And then the data I'm particularly focusing on is this low deuterium group of quartz monzodiorites down at the very bottom. But let's move to a different figure that's a little bit easier to read. Okay. Click. There we go. Okay. So this plot is similar to the other plot, but I've averaged all the existing apatite data by sample. So each point represents one rock. And some of these trends become much more evident when you take out some of the scatter by averaging the data. So I've plotted the delta deuterium range of Earth's mantle plus 60 to minus 140 in blue lines on this plot here. And what immediately jumps out is this little group down here of moon rocks with apatite with a delta D similar to Earth's mantle. A couple of basalts and some more evolved compositions in here. There appears to be another group, another potential reservoir up here with moderately elevated delta deuterium and low water. Many of these are evolved compositions, such as the felsites. There's also troctolite. Then you have the Mare basalts up here. Now, the Mare basalts were somewhat confusing at first because they're very enriched in deuterium. It turns out that enrichment in deuterium was shown by Romain Tartès that it is generated from degassing. When you erupt a basalt into a low-pressure environment, you lose water, you lose hydrogen, and you leave behind deuterium. So the Mare basalts would have started somewhere down here, around 100 per mil, near the range of the Earth mantle, and then degassed to reach these extremely high delta deuterium compositions. And then you have my rock down here, 1540455, with an average delta D of about minus 500. So the data I'm going to be showing today builds on this, confirms that this low delta D value is in fact that low. But before I get into that, I'm going to talk more about Apollo 15 quartz monzodiorites. Here we go, I think. Aha, okay. These are backscatter electron maps of two of the three quartz monzodiorites I've looked at, 1540455 and 1540451. They're sister thin sections from the same sample, although the scale is slightly different here. Major phases include pyroxene is the lightest gray, plagioclase, silica are the darker phases. The bright phases are ilmenite or phosphates, both whitlockite and apatite. All the pyroxenes have these beautiful exsolution lamellae showing that they formed in an intrusive body, probably through silicate liquid immiscibility of a creep basaltic magma. They're also they're fragments of an impact melt. Here's the igneous clast here, and then this is impact melt on its side. These samples were probably derived from Apollo sample 15405, which they were sampled as a soil from on top of the boulder that 15405 was sampled from. All right. So the Apollo 15 quartz monzodiorites are rich in rare earth elements, richer than in rare earth elements than even the classic creek basalt 15 through 86. They have a young exposure age. We know the exposure age based on the fact that they were collected from on top of this boulder, 15405, which is an impact melt breccia, and has an exposure age of 11 million years. So we do our measurements on the University of Hawaii IMS 1280 ion microprobe. And the data we were trying to confirm as being good was data we took at the Open University on their nanosims. Nanosims is excellent because you have a very small spot size, so you get really good spatial resolution. But your signal, because you have smaller spots, is much smaller, so the uncertainties are quite large. We decided to measure these rocks on our sims because we had grains that were big enough and because it would help us constrain the error bars a little bit better of the nanosims data we got. And thankfully, everything is very consistent. We calculate the water content of the apatite using H2O to hydrogen over oxygen 18 calibration curve calibrated to terrestrial apatites. So what did we find? This is my giant apatite plot again. I'm going to show the averages one in a minute, although I only go out to 2,000 ppm H2O this time. My new data is down here. The blue triangles are the quartz monzodiorite I showed at LPSC, and the yellow diamonds are the new data from 1540451 and 1540371. Everything is very consistent with what we showed at LPSC with a very low delta deuterium value. So this plot is just an enlargement so you can see the spread in the low water data. I only go out to 350 ppm H2O this time. This is all of my data from several different rock types. This is the cluster down here of the Apollo 15 quartz monzodiorites. You can see the very small error bars compared with some of the other data in the 1540371 and 1540451 samples. We found that it's consistent with these low delta deuterium in 1540455, and we even extended the lowest measured apatite delta deuterium on the moon to -750 per mel. That's incredibly low. It's only about 100 or so off of the protosolar value of -870. So where could this low delta deuterium material have come from? Well, the range we see in delta deuterium from about -450 down to -750 also happens to be very close to the range seen in agglutinate glasses. Those glasses are known to have incorporated solar wind hydrogen into them, which is why they're so light in deuterium. We know that these igneous rocks could not have incorporated solar wind hydrogen in them during their formation because they formed at depth in the crust several kilometers down. They wouldn't have incorporated solar wind when they were sitting on the lunar surface because solar wind can only penetrate less than a micron into grains sitting on the surface, and it can only diffuse less than a nanometer into the grain at lunar surface temperatures. However, these rocks are derived from impact melt 15405. Could solar wind hydrogen have been incorporated during the formation of that rock? So 15405 is thought to have been thrown to the Apollo 15 site as a result of the Aristillus impact. Aristillus is a 50-kilometer crater and would have produced impact melt, which we see in the matrix of this rock. However, it was quite a big impact, so it's not entirely clear. We were talking to David Kring yesterday, whether or not any regolith that was exposed to solar wind would have actually been incorporated into that impact melt. However, if it was, it would have had light hydrogen in it from solar wind. However, 15405 is extremely class rich. This is about a 2-centimeter image of a thin section of 15405, and you can see there are a lot of silicate clasts in there. It would have cooled quite quickly. Whether or not apatite as fragments, loose fragments in the melt, in the impact melt, would have been exposed or would have had time to equilibrate with anything with light hydrogen in the impact melt is unclear. And whether or not hydrogen could have diffused through the silicate material that surrounds our apatite grains is also unclear. We're working on the modeling now to see where it is. So this is a thin section, this is an image of 1540451. The apatite grain is up here. So it's several hundred microns from the edge of the section, from the edge of the impact melt. So it's not clear whether or not that hydrogen would have been able to diffuse through all that silicate and get into our apatite to affect it. We think it's unlikely. So what does this low delta deuterium component really mean? This is the average plot again. We have the Mare basalts up here, evolved rocks here, and then this cluster down here in the Earth mantle range. The 2 Apollo 15 quartz diorites. And then I've added the protosolar hydrogen range around -870. It looks like most of the moon's material, remember the Mare basalts would have started somewhere down here, have an approximately chondritic, would have started with an approximately chondritic delta deuterium around 100. This group over here, the moderately elevated moderately elevated deuterium evolved rocks, could be something different. We need to do more measurements to really make sure these are all resolvable from each other. However, these 2 very low delta deuterium samples are clearly resolvable from everything else. So it's possible they could have incorporated primitive hydrogen, maybe protosolar hydrogen, and somehow that component would have survived both the moon-forming impact and lunar accretion. Is that feasible? Lydia Hallis has been doing work on terrestrial Baffin Island basalts, which have the most primitive helium-3 to helium-4 ratios of any samples on Earth. They're from deep in the mantle. She's been studying melt inclusions in these Baffin Island basalts, and what she's found is that the melt inclusion, the delta deuterium of melt inclusions in those Baffin Island basalts are in this green ellipse here. They already extend to about 100 per mil, less than the known terrestrial, less than -140, which is the range lowest value in the terrestrial mantle right now, as low as -225. They seem to be trending downward towards an even more primitive end member somewhere in the Earth's interior. So it looks like the Earth managed to preserve a reservoir with relatively primitive hydrogen. So we think it's not unfeasible that the moon might have also preserved primitive hydrogen somewhere in its interior. So to wrap things up, low delta deuterium in the lunar interior could represent a primitive source such as protosolar hydrogen. However, we do need to do some more modeling to make sure that we aren't looking at hydrogen from solar wind. We're fairly confident that we're not, but we need to really do the calculations thoroughly to be sure. If this is a primitive component, it largely avoided fractionation during the moon-forming impact and lunar accretion. And based on all these data and apatite for delta deuterium and water content, it looks like there are several reservoirs in the lunar interior. I'll take questions.
Okay, thanks a lot. Looks like Larry had his hand up first.
Larry Taylor, excellent talk. I agree with most of it, except for the idea that the solar wind couldn't diffuse in. If you remember, we had that rock 14053, in which we showed that there was a gradation in solar wind impregnation over several centimeters. So I think it's possible. And also to think that these samples that are laying on the surface have not undergone all sorts of secondary metamorphism in processes during the micrometeorite impact. I think that there's a lot of heat types of metamorphism that are going on generated by the space weathering process itself. So I'm still in favor of the hydrogen diffusion.
Okay, we'll take a closer look.
I think Clive was next. Oh, okay, we'll go here first.
Clive Neal, Notre Dame. I almost agree with Larry, but the critical thing here is the amount of water you have there is very low.
Yes.
And I'm wondering, have you looked at the process of immiscibility in terms of most of the water should go with the ferrobasaltic portion? Mm-hmm. And I don't know of anybody that's looked at hydrogen in this effort, mm-hmm. but could be that you've enriched it in the lighter isotope and most of the heavy's gone in the runnier, in the more or the less viscous portion of that immiscible product.
We've measured cell sites that were thought to have been formed through silicate liquid immiscibility. 77538 in particular preserves both end members. We only found apatite in the ferrobasalt portion. It's low in water, very low in water, about 180 ppm, and relatively elevated. I actually showed some of the data on these plots, a delta D of about 400 per mil. We also measured data in 14321, or we also measured apatite in 14321, and found very low water, more like 80 ppm. And we did a lot of those measurements with the nanosims, so the delta Ds are kind of all over the place with high uncertainties, but they also seem to be somewhat elevated. So this Apollo 15 QMDs seem to be quite different.
Okay. Sorry, could you ask her later? It looks like we've got to go on to the next talk. Thank you.